All right, let's talk about a big name in the world of forecasting. ARIMA. Now, I know that acronym might sound a little intimidating, maybe like some complex piece of lab equipment, but really, you should think of it more like a time machine for your data. It's a powerful way to use patterns from the past to get a surprisingly clear look into the future. And that really gets to the heart of it, doesn't it? The big question, can looking backward really help us see what's coming next? Well, when we're talking about time series data, things like weekly sales, stock prices, you name it, the answer is a definite yes. That is, if you know how to listen to what the data is trying to tell you. So here's our game plan for today. First, we're going to learn how to read our data's memory. Then we'll use that to build our first predictive model. After that, we'll figure out how to stabilize messy data, put together the full ARIMA toolkit, and finally, we'll even learn how to tackle some of that real-world volatility. Okay, let's start right at the beginning. Before we can even dream of forecasting, we have to understand the hidden relationships inside our data. And that first step is all about learning how to measure its memory. The main tool we use for this is something called autocorrelation. Honestly, the best way to think about it is like an echo. It measures how much of today's value is just an echo of yesterday's value, or the value from 2 days ago, or 3, and so on. It's all about how a series relates to its own past. So, how do we actually see these echoes? Well, we use a special chart called the autocorrelation function plot, or just ACF plot for short. This thing is basically our map to the data's memory. It shows us, visually, the strength of that echo at different time lags, 1 week ago, 2 weeks ago, and so on. And the key is knowing how to read this map. On an ACF plot, you'll see these boundary lines. If a bar for a certain time lag shoots past those lines, it means the relationship is legit. It's statistically significant and not just some random fluke. For example, in one sales data set, the correlation at a 1-week lag was negative 0.43. So what does that actually tell us? It suggests a good sales week is often followed by a slightly slower one. See? The past is already giving us clues about the future. Okay, so this is cool, but how do we actually use it? Now that we can read the data's memory, we can build the very first piece of our model, the R part, which stands for autoregressive. But first, and this is super important, we need to talk about a concept called stationarity. A time series is stationary if its basic properties, like its average and how much it bounces around, stay consistent over time. Think of it like a calm, predictable river versus one that has crazy seasonal floods and rapids. We can only build good, reliable models on that calm river. And this visual really drives the point home. On the left, you've got a stationary series. It just kind of hovers around a stable average. But on the right, that non-stationary series has a clear trend, right? It's obviously going somewhere. Our goal almost always is to get our data to behave like that predictable series on the left before we try to model it. Now, once our data is stationary, we can bring in the autoregressive model. The simplest one, called an AR1, looks like this. And I know it's an equation, but it's simpler than it looks. It's just saying that today's value, yt, is a mix of 3 things: a baseline constant, some fraction of yesterday's value, and a little bit of random unpredictable error. We are literally regressing the series on its own past values. So what's the big payoff? Why do we go to all this trouble to make sure our data is stationary? Well, because it gives the model a very special and very useful superpower. Let's just watch it in action. Let's say a series has a long-term average, its mean, of 100. But then some random event happens and the value shoots up to 120. So what happens next? Well, because the model is stationary, it has this kind of gravitational pull back towards its average. So after just 10 periods, that value has already dropped from 120 down to about 103. You can see it's being pulled back to its center. And if we jump ahead to period 25, boom, it's almost perfectly back at its long-term mean of 100. This is called mean reversion, and it's the bedrock of stable forecasting. A non-stationary series wouldn't do this. It would be explosive, just flying further and further away toward infinity. Okay, so that covers the AR part of ARIMA. But what about the other letters, the I and the MA? Well, these are the tools we use to handle data that isn't so perfectly behaved right out of the box. The I stands for integrated, which is really just a fancy way of saying we use a technique called differencing. Let's say your sales are trending up every single month. Well, the raw numbers aren't stable. But what if you look at the change in sales from month to month? That series of changes might be totally stable. That's what differencing is. It's a clever trick to remove the trend and reveal the stationary signal hiding underneath. And finally, we have the MA for moving average. This part gives the model a short-term memory, specifically for surprises. So imagine last week's forecast was way off because of some sudden one-time event. The MA component notices that past mistake and uses that information to adjust this week's forecast. It helps the model correct itself quickly after random shocks instead of thinking a new trend has started.
So, there we have it, our three building blocks: autoregressive, integrated, and moving average. Now, let's put it all together and see how an ARIMA model actually gets built in the real world.
The classic Box-Jenkins methodology gives us a really clear step-by-step recipe to follow. First, you identify the data's features with tools like the ACF plot. Then you transform the data to make it stationary. You try out a few potential models, check out while they perform, see if you can make them simpler, and finally, you choose the best one. It's a really structured and powerful process. And, it's pretty interesting to see how ARIMA isn't just some isolated technique. It actually fits into a whole universe of forecasting methods. In fact, some specific ARIMA models are mathematically the exact same as other famous methods, like simple exponential smoothing. It just goes to show how universal these underlying patterns really are.
But there's one more real-world problem we need to talk about. What if the average of our data is stable, but its volatility, the size of its up and down swings, is changing all the time? This happens a lot with financial data.
For this exact problem, we have a special power-up, GARCH. Okay, I know, that is a mouthful, but all it really means is that we add a second model that runs right alongside our main ARIMA model. So while ARIMA is forecasting the actual value of the series, the GARCH model is busy forecasting its variance. It gives us a much more complete picture of future risk. Okay, let's wrap this up with the most important takeaways. First, the ACF plot is your map. It's your go-to tool for figuring out your model. Second, remember that ARIMA models demand stationary data, so transforming your series is often step one. And finally, when the volatility itself starts changing, GARCH is the tool you need to add to your toolkit. And that brings us to one last crucial piece of advice. Even when we have all these powerful, complex tools at our fingertips, the best forecasters live by a simple principle. Keep it simple. A lot of the time, the most elegant and easy-to-understand model is also the one that works best. After all, the goal isn't complexity for its own sake, it's clarity.